right, there we go. Okay, so I got a couple of slides to discuss here in terms of, kind of what I've been working on, and then some, future type stuff. What's coming down the pipe, basically. And there is something that I want to discuss, but I guess we'll see, how many, what sort of input we have here. All right. So without further ado, yeah, I'm basically talking about three different things. First, I got some status updates in terms of what I've been working on, primarily Stratix 10 device support. I have kind of a list of things that I want to get done for, kind of an eventual stable release. This is kind of a long-term, just kind of FYI sort of thing, just to make sure everybody's on the same page. I've definitely had a couple people ask about, can we start doing version numbers at some point and whatnot? And I would definitely like to do that, but I want to get basically the interface to the driver stable. And then I think it'll make sense to, start doing version numbers. And then for the time being, just use git master to keep things simple. And as part of that, the descriptor formats need to be kind of thought about a little bit in terms of, what the kind of long-term format is going to be. Because the way it's set up right now, it works, but it's also kind of a giant hack at the same time. So it would make sense to switch to something better that's going to work well, in the long term. All right, so let's see, what have I been working on? What's done? What am I going to be working on in the near future? So the kernel driver coding style update, I think I'm finally done with that. I'm not sure. The guys at the kernel driver experts are going to have to chime in and let me know if I've missed anything that I need to fix, but I think I've got everything. I think I got the PHI updates all done on all of the Corundum designs. I haven't pulled that back into the main repository yet, but I've tested everything 10G and 25G and everything seems to work. I've been working on the Stratix 10 H-tile, L-tile support. So this is all Stratix 10 except for the DX. The DX has the P-tile. But yeah, that's looking pretty promising at this point. And then some stuff I mentioned previously that I'm going to be working on next as soon as I get the Stratix 10 stuff out of the way in terms of the kind of PHI layer control and status registers, and then the 10G and 25G switching, so you can dynamically switch between those line rates. And then also the shared interface data path. That's kind of next up on my to-do list. I got a number of modules that need to be put together for that, so that's been taking a while to get that squared away. All right, so kernel coding style update. Talked about this a bit previously. Basically, I'm updating the all the C code for the kernel to match the Linux kernel coding style, and I figure I might as well, get this all cleaned up sooner rather than later. If we eventually want to get potentially the kernel module upstreamed into Linux, we'll definitely have to fix it. So might as well do it now. So the way it stands right now is I've fixed most of the checkpatch.pl complaints. I left a handful in there. Obviously, there's nothing we can do about the kernel version checks, because checkpatch.pl just says don't do it. If you're going to be committing it to the kernel, yeah, I mean, it makes sense. But if we're maintaining it out of pre and allowing people to use it on stuff other than the current mainline kernel, then you kind of need those. So and then there's a couple of files where I basically just ignored some of the complaints, because eventually the idea is to remove those files, and I'll talk about that in a bit. And so at this point, I think I'm done with this, but I think the folks at the MLE and possibly some of the other kernel development experts will have to let me know if I've missed anything. So, but yeah, it's pretty much squared away at this point. I think if there's anything left, it's going to be, minor. All right. So I've also got ahead and, like I said before, I was working on the PHI update for the PHI integration changes on all of the 10G and 25G designs, where I'm replacing the, monolithic GT Wizard instance that has, one GT Wizard instance for all of the channels with wrappers for individual channels. Big thing is I figured out there's a TCL command that allows you to turn off the placement constraints for the GT channels. and then you let the pinout constraints, get everything connected properly. So that's been updated on all the devices. I'm going to have to do some additional work to this again for the 10G 25G switching, but that shouldn't be that big of a deal, I don't think. But yeah, at this point for 10G and for fixed 25G, it's all updated. I haven't pushed it back to the main repository, but it's all updated on my development fork right now. All right, and then the big thing I've been working on over the last week is the Stratix 10 H-tile and L-tile support. So for various reasons, this is going to be necessary in Corundum, primarily because the new testbed that we're putting together for the research at UCSD uses these Stratix 10 MX development boards from Bitware, the 520 and MX boards. And the folks at MLE apparently are also using or considering using Stratix 10 for one of their products. So I've prioritized this just to cooperate with the folks at MLE, and hopefully if I can get things into a state where they can take over, then potentially that'll remove some work from my plate if they can help out with some of that. So I've been making a lot of progress there. So previously I got the Ethernet interfaces on the Stratix 10 operational on both the MX and the DX. So I have my Stratix 10 MX development kit, and then also the Bitware board, and also a Stratix 10 DX development kit. So let's see, I guess just yesterday I got the Ethernet design, just the Verilog Ethernet test design running on the Bitware board. But previously I had it working on the other two. So everything works at 10G. I have not done any testing at 25G or 100G yet. So we'll start with that, get things working, and then try to bring up the other interfaces. And then for PCI Express, I've been working on the hard IP model in CocoaTBX PCIe for the H-tile and the L-tile, which are found on most of the Stratix 10 devices except for the DX series. And that's been committed to CocoaTBX PCIe because I think I have all of the main interfaces working. So, flow control, transmit, receive, interrupts, and some of the, there's like a configuration space time multiplexed output. So that also works as far as I can tell, and matches what the hardware is doing, or at least the parts that I'm using that matches what the hardware is doing, because the test design works. I also put together a an interface shim for these devices to adapt to the generic PCIe interface. So this works at Gen 3 by 8. Extending it to Gen 3 by 16 is going to require some additional work because it uses a segmented interface on the PCIe hard IP side. So we'll get it working at Gen 3 by 8 and then circle back around to that a little bit later. And I got the Pca Example Design, which basically just brings up the DMA engine and does a couple of very simple tests running on both the Stratix 10 MX dev kit and the 520N MX. And it does close timing. I had to make a couple of changes to the code in terms of adding some directives for Quartus so that it actually instantiates distributed RAM properly. If you don't do that, then it fails timing horribly because it's using far too much block RAM. But yeah, with the conversion to, or with the addition of these constraints, so it actually infers the distributed RAM correctly, which are called MLabs in the Intel parlance, then that actually works. Okay, so then the next step is to run the DMA benchmarking design and then Corundum. So the DMA benchmarking design is going to be a bit more stressful than just the example design, which I think runs a grand total of like 1 or 2 DMA operations. The DMA benchmark design will run, a large number of them, just to make sure that we've shaken everything out. So the test bench for that runs, but I need to do a little bit of cleanup work before I can actually run that on the device. One thing that I realized is that I didn't really build the shim correctly on the transmit side, and that it's possible to not provide a TLP contiguously to the hard IP core on transmit. So I need to do some reworking to fix that. And then I'm going to try the DMA bench design. So hopefully I'll be able to do that early this week. And then for ancillary stuff for Corundum, Flash access, I2C, that sort of thing, I'm going to leave that as to do for now. And the Flash access, that's going to be a bit of work. I guess I should actually ask the MLE guys for the product that you guys are working on. Presumably, you guys are going to want to do firmware updates over PCI Express for the Stratix 10. Not sure about that. I guess we'll get back to that. I need to take a look at exactly what that update process is going to look like on the Stratix 10, because I think it's a little bit more complicated than on the Xilinx devices, because the Intel devices have this secure device manager block, and I think the flash access has to go through that in some way. I'm not quite sure. That could complicate things a little bit. So I'm going to leave that as to do for now. And then for the I2C, I'm planning on sitting on that until I have the little microcontroller operational on the FPGA, and then we'll implement I2C through that. But yeah, so that's what I'm working on now. I'm definitely making forward progress here, but there's a few things that need to be cleaned up. All right. Does Emily have any comment on firmware updates on the Stratix 10?
Yeah, I just had one, but I was muted. Sorry. I guess you want to do this, but actually, so as we will use custom built hardware, I guess we need to make sure, or actually, yeah, design it in a way that it makes sense for us to do. So this is not done yet. So maybe it makes sense to do it similar as it is done on the bitware board, right?
So the thing that really annoys me about the Intel boards is, for whatever reason, they like adding these little max 10 FPGAs for various reasons. And the way that's done can be quite different from board to board. And apparently it's not absolutely necessary, because on the Stratix 10 MX development kit that I have, the Stratix 10 FPGA is directly connected to just a QSPI configuration flash. So that's like, there should be no problem there, because you're directly talking to the flash. You can read from the flash, you can write to the flash. Presumably, it shouldn't be that big of a deal. So that is a reference point saying that this is definitely done on at least one Intel FPGA board. So presumably you guys would be able to do the same thing. It's just directly connect the FPGA to a QSPI flash, and not have to add any additional FPGA, and then you can just load from there. So that board does have a max 10 on it, but I think they're only using that for the USB JTAG. For the bitware board and the Stratix 10 DX dev kit, the max 10 sits in between the main Stratix 10 FPGA and the configuration flash. So the FPGA cannot directly access the configuration flash. On the Stratix 10 DX, I don't think it's possible for the Stratix 10 FPGA to access the configuration flash at all. Like, the only way to update the flash is to go in over JTAG and go through the max 10 FPGA to update the flash, which is just stupid. And then on the bitware board, they implemented it's basically set up the same ways as DX dev kit, but they implemented some proprietary pass-through basically that allows the FPGA to send commands of some sort to the max 10, which will then go and perform an operation on the flash. So I need to figure out exactly what that looks like. Fortunately, I have the source code for the firmware update tool that the bitware uses with their example design. But most of that firmware update process is handled by the HDL side. So they have a big block that connects to their PCIe DMA subsystem that is responsible for writing the firmware out into the flash. So it's basically what happens in the driver side when you want to update the firmware is it basically creates a gigantic mapping in memory where it writes the entire configuration bitstream, and then it points the firmware update block at that, and the firmware updater reads it via DMA and writes it out into the flash using this. I think it's some sort of a streaming interface to the Max 10 FPGA. So it's kind of a screwy setup. So I think for most of the Xilinx boards, it's like a direct connection to the flash from the FPGA. So it's pretty straightforward. But for the Intel ones, it seems like there's going to be a lot more variety in terms of what needs to be done. So we might need to do some ruminating on that to figure out what's going to make the most sense. On some boards, it's not going to work at all. Like the Stratix 10DX dev board, you can't update the firmware from the FPGA. I think the reason for that is that Intel has their CVP thing, and they're like, yeah, just use that. And it's like, okay, that's nice, but there's stuff you can't change via CVP, like the PCIe device and vendor ID settings and whatnot. And then you also have to, ship the bit file, alongside the driver, and it adds some logistical complications. So I don't know. We can probably circle back to that later. But the main question is, if that's something that you guys are interested in at MLE, that would be useful, because then you guys can get up to speed with that, and we can collaborate on that instead of me just doing everything myself.
Yeah, of course.
Sense.
Yeah.
All right.
Let's get back to this later on.
Yeah, sounds good. Sounds good. All right. So let's see. What else do I have? So that's basically it in terms of status updates. I have a couple of slides here in terms of the PHY CSRs, but I showed these last week, nothing particularly new. So the PHY CSRs, what I want to do is add some registers that allow you to kind of view the status of the PHY layer components, and also potentially change some settings. So, we want to see link state information like block lock, auto negotiation status, loss of signal indication, things like that. And then also provide some pathway for controlling some link settings, such as resetting the transceivers, controlling FEC settings, transmit disable, changing the link speed, which is necessary for the 10G, 25G switching, and things like that. So I need to come up with a kind of format for these registers and figure out where I'm going to put them and whatnot. And I may also need some sort of driver accessible mapping, so you can see which ports on interfaces, on which interface is connected to which PHY. So a couple of things that need to be squared away with respect to that, but shouldn't really be that big of a deal. And then once that's operational, then 25G switching, so you can take the 25G links and drop them down to 10G. Presumably this is just a case of getting 2 PLLs running. I did a little bit of poking around at this. It looks like I'm going to have to be implementing my own reset networks, because the kind of reset components that are built into the GT Wizard are very simple and not very configurable. Like, they're really only set up to use one PLL. So if you have 2 PLLs, you have to do the reset networks, yourself, so that you're looking at the correct PLL locked signal and yada, yada, yada. So I got some ideas how to do that, but I got to sit down and write a couple of simple state machines and whatnot, so all that works correctly. Shouldn't be a big deal. Yeah. It's like, even though the GT Wizard has an option for configuring a second PLL, it doesn't really have any support for switching between PLLs. It's just set up, statically, we're going to use this one. So if you want to switch, then you have to do everything yourself, which is slightly annoying, but what are you going to do? All right. And then I also have the shared interface data path that I'm working on as well. That'll be kind of the next thing. I don't have a slide for that at the moment. I might have had one before, but I removed it. Okay, so that brings me to kind of the to-do list for a stable release. Right now, I consider Corundum like alpha, basically, super in development. I'm definitely planning on making some breaking changes to the driver interface and whatnot. But once some of these changes have been made, then we'll be in a position where we can actually try to version stuff and develop components, more independently. Like if we actually wanted to have a DPDK driver or something, or get some of the drivers upstreamed into DPDK or Linux kernel or whatever, then it'll actually be a little bit more reasonable to do that once the interface is a little bit more stable. So let's see, the to-do list consists of several things. First one is application section. That's, well, it's not completely done. We still have some more integration level work to do on the kernel module, but in terms of what's going on the FPGA by providing this additional bar and whatnot, and the connections of the HDL, that's all done at this point. Although we may be making a few adjustments to that interface as the rest of the design evolves. It's at least done enough to qualify. And then the next thing is a shared interface data path. This is going to be necessary for things like RDMA. It's going to affect the register layout by moving, by shuffling a few things around. I think the main idea here is that the port control registers are all going to get kicked up into the interface. That's the main thing that kind of affects the reason the shared interface data path is on here. But that's also kind of an architectural change. So, we might as well get that done, and then everything will be built on this new setup. And variable length descriptor support. I'm going to talk about this in detail in the next couple of slides, but variable length descriptor support will provide some performance improvements and some flexibility improvements, which is going to be, incredibly useful in the long term. It's going to be necessary for RDMA support and whatnot. But it is going to totally break all of the current driver interface. So yeah, it would make sense to get that squared away and get that all, operational sooner rather than later. And basically the current descriptor format is a little bit of a hack, especially in terms of how the scatter gather is currently implemented. So, a long-term solution is to, do this correctly and do this in a more flexible way. So until that's squared away, I definitely don't want to, get stuff upstreamed where it's going to be hard to change. And then I also want to do some reorganizing of the register space a little bit. I think the large part of this is not so much about actually moving things around, but providing a more scalable, more flexible way of exposing kind of offset information. So right now I kind of have a fixed set of registers that's like this particular location is the offset for this particular thing, but coming up with something that's a little bit more general. So instead of just having fixed locations for fixed things, maybe having some sort of an ID number that indicates what the offset refers to. And this will allow you to add more functionality later, or swap stuff out in a way that that's going to be a little bit more backwards compatible, right? Because an older kernel module would just, it wouldn't understand what these options are, and it can just ignore them. So like if you're adding some diagnostic capability or something like that, that the driver doesn't really need to poke at, you can expose offsets that, your user space code can look at. Ulrich, did you want to add something?
Yeah, so I guess we could have a discussion about this one, because we did build about, I don't know, 3, 4, 5 PCI Express devices in the past, where we added, some kind of like the PCI Express configuration memory exposes blocks within register spaces of devices to organize and provide various features or data, for status control, monitoring, whatever.
Yeah, I mean, that's why I'm talking about this here, because if people have input, now is the time. So yeah, that would definitely be interesting to look into. So you're talking about, not through configuration space, but through the bars.
Right, but
okay.
the way to do this is kind of the same as the extensions of the configuration space is organized. So usually you have kind of an ID and an offset and the next offset or something like this, so that you have a list of blocks.
You're basically building up a linked list across all of the
right.
Components. Yeah, so I was thinking about doing something like that, but the concern I have with doing that is now each thing that you're attaching in there has to have this little header attached to it, which now means you don't have a nice, factor of 2 of address space for each one of your components, right? So if you have a component that needs like a megabyte of address space because it has an internal memory that's a megabyte in size, well, now you need to bump it up to 2 megabytes just because of this little teeny tiny little header that you're attaching on there. So I was thinking about doing something a little bit different where we have a list in one spot that then points to all of the regions somewhere else,
I
instead of
guess that,
doing a linked list thing.
yeah, I think you can combine this. You could, for example, provide an entry that just has for this specific, let's say, memory area. You could just have like 6 registers, the ID, the next pointer, the size of the memory area, and the pointer to the memory area. And then the entry is just, no, I think it was just 4 registers. And the memory space is somewhere else again.
Okay, I
Right?
see what you're getting
It's
at.
just about how you
you'd
could
have a
discover
linked list of
this.
all of these headers, but the headers would be
Right.
separate from the actual regions that they're describing.
Yeah. And
Okay.
you could do this hybridly. So if you just have, I don't know, a counters list, you could say the byte counter of various internal interfaces. You could either go with, this is the entry for providing the counters, and then it's just an array of counters because it's known to the driver how many these will be because of another block, for example. Or
Right.
you could go with have a look at the counters over there and do this indirectly. I think you could do both, but the important part is if you do this with linked lists or similar items, it's very flexible and you could easily discover this. And if you change something, you could also go with version numbers of the blocks itself, for example. You can say, okay, this is a statistics block. Oh, it's version 2. So I pull out the code to deal with version code with the version code 2 statistics block. So it's very flexible and modular.
Okay. Yeah, I think that makes a lot of sense. Okay. So basically
So
doing
I'll see
similar to
whether we can provide you with a documentation of one of our device implementations. You could just have a look at it and maybe you get an idea about what we did.
Yeah, that
This
sounds like it
works.
would be a useful thing to look at, and that could be useful probably in a number of different concerns too. Like for the firmware update, for example, then you could indicate, what exactly what the interface is, and then if you have different devices that need totally different techniques, then you can indicate that. Because right now it's
Right.
basically I'm just using a couple registers for that, and they're at fixed offsets, and one of them is kind of an ID register that then indicates what the interface is. Is it SPI or is it QSPI or is it BPI? But yeah, doing something a little bit more scalable, I think, would be or a little bit more expressive. I think would be a
Right.
good idea. Yeah.
Yeah. I'll check. I think this documentation is not public, but I guess I'll discuss this internally if we could just provide this to you and ask you not to provide it to somebody else.
Yeah,
then we're
or if you
fine.
just want to give me a couple of pages or something, not the whole thing,
Yeah.
but
Okay.
yeah,
Makes sense.
that would be fine. Because I don't need to know what your device does necessarily, but just having a listing of what a couple of these blocks looks like, just at the struct level, basically, would probably
Right.
be enough to get the point across.
Okay. Yeah. And otherwise, yeah, maybe in the next dev meeting, Joachim will also show up again. So he was one of the implementers of this
Well, he's
device.
on the list right now. He's on the call right now, it says, but I don't know.
Oh,
I guess
I
he
did
doesn't
miss
feel
him.
like adding anything. Or maybe he's double or triple muted or something.
Oh yeah, he is there. Maybe
I guess he
his
doesn't have anything to
special
add.
configured mute button doesn't work for the Zoom meeting.
Yeah, perhaps. Oh well, I guess we can discuss that a little bit more in depth later. But okay, so it's sounds like you guys
Okay.
have some ideas. Oh, Jashin?
Yeah, so yeah, like I have one small idea, but not for like we need to implement in Corundum, but the things is when implement the user space driver or even in the kernel space driver, there is one bottleneck, which is the MMIO bottleneck, in which, like for example, the CPU can only read the NIC register in 10 Mbps, otherwise the CPU will stall. So one interesting design we would discuss is currently all the things is the software reads the NIC register. How about when we update the pointer, we can use the NIC to DMA the pointer into a specific memory region in the host, and the CPU just read that memory region. So these are two design choices. So I just want to know, how do you think about this?
That's a good point. Yeah. That's actually something I'd forgotten about. That was mentioned to me a while ago. With I think the guys who were doing they were doing some simulation stuff with Corundum. I'm drawing a blank on the name of the paper. Oh, Simbricks. That's right. Yeah. And they had mentioned that this was a problem that they had discovered in Corundum that was causing a significant performance bottleneck in their simulation and slowing things down a lot. So yeah, I'm not sure.
So if I could interject a little bit, the
Yeah, sure.
design that Jiachin just expressed is found in the Intel 82599, presumably later. It's just a configuration option. So it seems pretty sane to reduce the one MMIO from a critical path. Maybe
right,
two.
Yeah. So that could be used for both the transmit and the receive path to, pass that status information back. Yeah. It seems like there's probably a number of NICs that do that. I think
so.
the Mellanox NICs may also do something similar.
Yeah, I'm sorry. I should have. The 82599 is kind of just like a baseline I like to use. I should have.
Okay.
There are many NICs that do this, including the 82599, which is a very old NIC. And so if a very old NIC does this, then I think we can assume new NICs do this too.
Right. Yeah. For doing that, I think the main thing is we're gonna have to store a pointer as part of the queue state for where we're gonna write this write these counter values, basically. So it's definitely possible. I guess the other component is how to do that with the DMA subsystem, and I did put a little bit of thought into that. Like if you just wanted to do single D-word reads and writes basically via DMA, what I may want to do is add kind of an AXI Lite interface to the DMA interface, so you can just say, hey, write this D-word into host address space here. I think that could be a pretty useful capability and could be used for this. So I think that's definitely something that we could do. I wasn't going to put it on the to-do list for a stable release, but at least factoring this into the design of the queue state code, so that that pointer will be available on the FPGA side, I think would enable this particular feature to work. So yeah, I think it definitely makes sense to implement that because it's going to help with the performance, I guess, for both kernel space and user space. So I think right now with the kernel driver, it's probably not that big of a deal because you're doing it's mainly MSI or waiting for an interrupt to come in, and then at that point, then you'll basically pull as you're pulling packets out. So you're not just busy pulling, but you'll check the counter. Okay, I have this many packets to work on. You'll crank through those packets, and you'll check again, see if there's anything more. So that's less of an issue than if you're just sitting on that, sitting on those pointers to see what happens.
I mean, I think you're raising a few things. One, we should probably look at the kernel driver interface and make sure it's only, so we have an interrupt, then we have the NAPI subsystem reading a batch, and probably be worth us going through and sanity checking that it's at least reading that register only once per batch and not once per packet.
Yeah, I think that's once per batch.
It should be once per batch because I
Okay.
definitely read it outside of the loop.
Yeah. Yeah,
So
but
that-
I mean,
That
so
then
it
begs the
seems
question
that-
of how much improvement do we expect from it? I think there are scenarios, especially low latency, maybe single packet processing it's going to really help with, but
Right. So I guess this does bring up the question of, throughput versus no, throughput in bytes versus throughput in packets, right? So right now I've basically been considering, most of the time we're going to be running large packets through Corundum. So I'm not going to care too much about packet rate, but
So I
if I
think
could get
this is maybe
100G
the
with
third-
with 1500 byte packets or 9K MTU packets, then we're doing pretty well. But if you
I
want to
think
crank it up for small packets, then
this impacts both, if equal size packet size, this impacts both bits per second and packets per second is equal because it's a packets per second issue. It's how many packets you get to read. But I was actually trying to say a third thing, in that you also just have no load latency. And this is a thing that is going to make a big win in no load latency.
yeah, right, because you don't have to wait for those MMIOs to go back and forth across the PCIe
Yeah.
bus.
And I
Yeah,
think
that's true.
performance is mostly going to be, I think, batch size dependent.
Right.
Yeah,
Yeah.
but I think all these things matters less in kernel space because I guess there are many overhead in the kernel. And these
Is it that
kind
it
of
matters
latency-
less, or is that performance is already bad, so you don't care if it's bad still?
I
Yeah.
think that was the point, right?
Yeah.
I mean,
it's not
but
that it's not that it matters less. It's just that you don't care about kernel because kernel's bad performance and you've already written it off.
yeah, that's true. So that's why I observe all this overheading when I implement the user space is because we are doing busy pooling and we have efficient CPU, then the bottleneck becomes the PCIe and the hardware. So that's why I observe. But I mean, for the stable release, I think these features may not need to come with it. But these design options are good things to keep in mind.
Well, right. It's definitely something to think about. And the other thing too is if there's people that want to kind of work on some of these features, then we can certainly discuss what would need to go into, what would need to be done to implement some of this stuff, and then I can, let some people loose on this.
Yeah, I mean, I guess I should. Sorry, I showed up late. I should introduce myself. I'm Brent Stevens. I'm a professor at Utah, working with Jiaqian. And I think that's exactly why I'm on this call. And so, I get that this isn't coming out unstable, but I'm just sort of here because we're working on it. We want to participate.
Yeah, well, I mean, that's kind of the whole reason I decided to organize these things. So people that are using Corundum can listen in or potentially, offer some feedback or potentially even step up to the plate and help implement some stuff. So yeah, great to hear from you.
Yeah, and I think that, like I said, the direction Jiaqian brought up is what probably going to be one of the first things we maybe look at.
Right, yeah. Yeah, so I think part of that also circles back to the variable length descriptor support, because in order to implement that, there's a whole bunch of stuff that's going to have to be rewritten. And one of those is kind of all the queue management logic. So when we go rewrite that, that's actually one of the things I was thinking about in terms of, what registers do we need? How are we going to organize it for all of the queue state registers? And, can we pack in another 64-bit pointer on a per queue basis and not, consume a huge amount of block RAM or URAM for the queue state? And I think there are some options there. I'll have to go hunt down the spreadsheet I was working on. But yeah, that's definitely something I've been thinking about, ways of implementing that.
I think, just since I guess I'm still having a conversation, and if I'm derailing something, we need to move on, let me know. But one of the things that caught my eye was, why are there 3 queues? We have the event queue, the completion queue, the receive queue. I think if we're doing a redesign, you might be able to get rid of one of those and save yourself some memory accesses. I think the other big pet peeve, or
Right. So
sort of-
with the multiple queue types, this is really based off of what the Mellanox NICs do. This seems to be I'm not sure if this is an RDMA thing or a Mellanox thing.
Mhm.
And if we're going to eventually add RDMA support, we're actually going to have to add more queue types. But potentially that can be mapped a little bit differently onto the hardware queues.
Yeah, I'm not sure about that. I mean, so the RDMA support has, every receive queue has a associated completion queue. And I don't think they have more queues than that.
So with RDMA support, you can actually have multiple receive queues feeding into one completion queue. The big thing is that the RxQ count and TXQ counts need to be the same because you're creating queue pairs, which are a combination of an RxQ and a TXQ. So right now, Corundum's not really set up that way to have the same number of RX and TX queues. But that would probably
This is just my take for a first implementation is don't do the general thing. Just have every TXQ as a CQ, every RxQ as a CQ, you're done.
Well, so we're going to change the whole interface again when we implement RDMA?
No, this allows you to, I mean, this allows you to implement a lot of RDMA programs, I guess. And I would say even you can in library, make it look like you're doing the multiple queue pair thing when under the scenes you're not. And I think it's a reasonable first.
Not really sure that's possible, but we'll see. Because the whole point with RDMA is that you can allocate the queues separately. Like there's separate calls for allocating RX and TX queues and a separate call for allocating completion queues.
Yeah, I mean,
So
but
I'm
so
not
I
sure how you
think
would keep track of all that.
I think there's searching for general implementation of the OFED. That's a good goal. I think implementing some programs in the OFED is another good goal. But I think so a CAQ isn't useful if it doesn't have an RxQ associated with it. I think I'll maybe, defer this until I go and look at the actual, OFED API again. But I think you can probably fake it and just know that all CQs are going to be associated with the TQ or an RQ. And so just like allocate them together. I'm not entirely sure. I think you have a reasonable concern, but I'm not entirely, especially if the pain is worrying about hardware. I think you can probably fake this in software.
Right. Okay. Well, I'll have to think about that. I mean, I thought you were going to say get rid of the EQs because the EQs are what are driving the interrupts.
Yeah, I was going to say that because you can include data in your interrupt and you're not including data in your interrupt right now.
What? What do you mean include data in the interrupt?
There's you can get 4 or 8 bytes along with your interrupt.
How does that work?
I'll have to look at the 8299 driver again. That's my baseline.
Right, because
this was like 3 years ago, so I'm sorry, it's a little bit rusty for me, but I played around with the 82599 a lot then.
Okay, so I've been looking primarily at the Mellanox 4 and Mellanox 5 drivers. So
yeah.
Because it's possible they're doing basically the equivalent of an event queue sort of thing there. In fact, that's the only thing that would make sense because PCI Express doesn't have a way of transferring any data associated with the interrupt.
You sure?
I'm sure.
Okay.
I've looked at this. For MSI, it's a single D word that indicates what the interrupt is. You're given the data and you return it back with the interrupt.
I think that D word is the queue the interrupt is for on the Intel driver.
Right. So I guess part of this is that right now I'm using MSI. We might want to consider moving to MSIX, which
they're using MSIX. They are 100% using MSIX for this.
Right. But I think there's still a limit in terms of how many individual interrupt channels you can have. I don't think the Mellanox device driver has an interrupt per queue. I think they have
but the interrupt handler that reads the D word, the Intel
driver
handler
does not read the D word. That D word goes to the hardware, the interrupt controller, and then that maps it onto the software IRQ at the operating system level. So you just get called with the IRQ number.
Yeah,
never
I
see
think
what
it
the
might
hardware
be the
writes.
IRQ number is per queue. They only have 128. I'll look into this. I think we should table it since it's a little bit outside of my
Mellanox
memory.
Mellanox supports thousands of queues, not 128.
I don't.
So, all right.
And then also, I'll maybe finish with the umbrage saying that the Mellanox Nick lies to you and saying it supports it supports a small thousands number of queues, but they lie to you about how many queues it actually supports.
All right, that's probably true. Yeah, in terms of, the API allows you to set up a lot, but it only, caches a certain number in hardware. And the rest are stored in some sort of a data structure in host memory.
Yeah, but maybe I'll table this. Sorry for saying that the software reads the D word, but I think the design, even if you have a D word that gets you 4 gigs, you can have an interrupt per queue.
Right. Yeah. So yeah, we can certainly take a look at that. Implementing MSIX, I think, is definitely something that's going to make sense. But I think that's still only going to give you, order of a few hundred, maybe 1,000 IRQs.
Yeah, and
again, I'll
that's
have to
where
do
my
the operating system.
exactly where I'm not willing to say yes or no or anything. But so I think you're onto something. As another pet thing, since I've got people's attention, the other thing that Mellanox Nick does that is almost like what I wanted to do in my paper Loom, but didn't. That's just the software implementation. Is doorbell queues. But
doorbell queues, as in, this is how software informs the hardware. That
yeah, I mean, so this is. Think of are you familiar with Blue Flame on the Mellanox Nicks?
I don't know. Well, let me put it this way. I've seen some of the code for it in the driver, but I don't know too much about what the hardware is actually doing.
Okay, so essentially, you've got your descriptor rings, you've got your descriptors, you can set up scatter gather. At some point, most NICs like these 82599 have then you update a tail pointer at the register specific for updating a tail pointer. Mellanox instead has what I'll call a doorbell register. And the doorbell register is probably an intermediate between a tail pointer and a doorbell queue. So a doorbell register, one of the things it lets them do is they've just added a little bit of custom hardware. So let's say you add a header, and then I can do my tail pointer update. Done. I updated my tail pointer. Let's say I want to send a 64-byte packet. I add a header, I send the 64-byte packet. It just immediately recognizes that as a packet and sends it. So it's somewhat for low latency. It's also useful, if you have your tail pointer per core, that gives you the parallelism like you currently have. But so just the more fully featured doorbell, rather than just having a proliferation of this is my tail pointer register, this is another register, this is another register. And that's fine. But I think the real power it gives you is some of the things they let you do with like inlining descriptors, inlining packets.
So is this, so I'm just trying to puzzle apart the difference between a descriptor queue, whatever that is, and a just updating the pointer.
Yeah, so there's 3 ways Mellanox lets you send packets.
Okay.
The first way is I write data in pinned memory. I write a descriptor with scatter or gather lists to that pinned memory. I ring a doorbell. That's normal. Okay. The other one way I can do that is I write my descriptor somewhere, or sorry, I write my packet to pinned memory, and then I create a descriptor, and that's what I write to my doorbell. One less trip, larger doorbell, MMIO data. The third way they let you see it is I create my small packet, I write the entire packet directly to the doorbell.
Okay. So this is a way of just sending the entire packet directly to the NIC via MMIO.
Also for inlining, it lets you do both. So it lets you do, I can send the entire packet, I can send a descriptor inline with my doorbell, or I can just send the tail pointer with my doorbell.
Okay, I see.
And this is mostly used for the high frequency trading psychos.
Right, yeah. So I guess maybe you're not entirely familiar with kind of the original design of Corundum, but
I'm
Corundum is
not,
not really
and I
designed
apologize for that.
for low latency. It's designed for control. So the whole point of Corundum is to allow the transmit schedulers to very precisely control all outgoing packets. So this kind of doorbell stuff, I have no idea how you would integrate that effectively in with the transmit schedulers.
Yeah, well, I mean,
it's
so
definitely
that
not
this is,
it would be like antithetical to what we're using the NIC for, because
I'm not
now we
sure
have to
I
store
agree
all
with
these
that.
packets on the NIC and keep them associated with the transmit
No,
queues they were
no,
sent out of,
no.
and yada yada yada. So
I mean, I will say I can. So I think there's a few things, but one, this ultra low latency, I don't think is antithetical to your work, and partly that's part of the beauty of optical, is that it gets you really low latency. And but so I think the other thing here is, from my work on Loom, I went so far as to then go and say that these doorbells are a good way to do fast configurations and fast reconfigurations, asynchronousy of your NIC. So I think this could lead to a better mechanism for programming your schedulers potentially. And I'm certainly not saying we put this in stable, but I'm not sure this was something that was even on the conversation. So
right. Yeah, it is an interesting capability that yeah, we might need to circle back around to that at some point and kind of figure out, how that might fit into the rest of the design. No, the reason I say it's kind of antithetical is because we're not necessarily shooting for low latency, we're shooting for control. We have to send packets at specific times, that are going to specific destinations. We can't just send packets whenever, because we have an optical switch that's going to be reconfiguring the links. So
I mean, I guess that's a bit weird thing, because it's almost like I'm hearing that it's okay to accept high latency, and that seems like, I understand that there are extra complicated with scheduling and buffering packets, but I thought that, as I see it, the goal is to build a good network, and at some point, we're building toys or research products, and we have to decide what's going to be the good network. But having an ability to do a low latency injection of a single packet into an optical rotor network is something that I would like to do on a rotor network.
well, you can't on a rotor network, but you might be able to do it on Opera.
Well, I mean, so maybe, okay, yeah, on Opera, I get, but so how about, the lowest latency allowable by the underlying fabric, right? How do I
Right.
get that packet to the head of my NIC buffer?
Right. Yeah, I mean, let me put it this way. If this is something that you guys would be interested enough to, help implement, then, maybe we can find a way to make it work. And it's always possible to implement something like this, with a switch where you can turn it on or turn it off depending on what you're doing.
Yeah.
So, potentially, yeah, and having the functionality there in hardware could certainly open up some other, potential paths, like you're saying, in terms of potentially reconfiguring schedulers or other stuff. That could be a useful capability.
Yeah, I think that's a good place to leave it. I don't want to make the meeting go longer, but no, I agree. It's not immediately what we're building first. It's not immediately what I think anyone should be building first. But I think it's at least good to have on the roadmap of this is a thing that could be useful.
Right. And then in terms of also providing the hooks for it in the driver interface and whatnot. So even if we don't implement it now, setting things up in such a way it wouldn't be a gigantic pain in the butt to implement later.
Yeah,
there's certainly something to be said for that.
Yeah, or I think maybe the thing we're talking about, reorganizing RX queues, TX queues, CX queues for RDMA, and I think it's probably worth at least making sure that this doesn't end up being incompatible with something like that in the future.
Makes sense. Yeah. All right. I guess I can finish up the slides that I have here, because after this I want to talk about the descriptor format a little bit. So all right, so let's see here, where were we? We're talking about the register space reorganization, right? And then there's also the on FPGA management softcore that I want to get operational, and the main point about that is to get rid of all of the board specific kernel code. And if we don't have any board specific kernel code, then that means every time somebody adds a new board, we don't need to update the driver. You just update the, you just edit the firmware running on the core to support whatever that board needs, and then you're good to go. overall goal is to stabilize the driver hardware interface, and hopefully along with this process, we can also document the driver and hardware interface. And then once that's done, then we may be able to, start attaching version numbers and potentially get some components of this upstreamed. But yeah, so that's kind of my list. I guess potentially we can think about some of these other features, not necessarily implement them, but make sure we have, hooks in here. We have the capability of, tacking some of these features on later, if that involves leaving some space in register spaces and address spaces in various places that we can make use of later. That would be reasonable, I think, for, a to-do list here. And then we can add, some feature bits and whatnot to indicate that some of these features are present and usable and yada, 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 down the road. All right. So moving on to variable length descriptors. So right now, so variable length descriptors, the advantage is that they're very flexible. You can put a variable number of pointers for efficient scatter gather. You can potentially include, inline packet data inside the descriptor, so you don't have to perform an additional DMA operation. So this can be useful for either for small packets or for packet headers. And you can potentially also put metadata inside of the packet headers, which could be handed off to, an accelerator or something like that in hardware. It's also relatively easy to add new descriptor formats. If you have a variable length descriptor, with type fields and whatnot, then, you can add additional fields and whatnot. It kind of falls under the metadata category as well. But yeah, it gives you a lot of capabilities. It's also efficient because you only send what is required per descriptor, right? So if you need to support scatter gather with up to, 4 or 8 or, some number of pieces, then you can send exactly as many segments as you need in each descriptor. But the disadvantage is that they're more complex in terms of, fetching and parsing, right? You have to parse the descriptors in order. You can't just, parse them randomly. And you have to read, kind of the maximum size block before you can start parsing. And you have to read ahead until, the end of whatever's in the current queue, or, at least one maximum size descriptor. And you need, ideally, would also be able to cache stuff for a while. If you read a bunch of descriptors, then you can keep those in the cache until they need to be, used for, until you need to free up that memory for something else. But all of these extra things that you need to do to support variable length descriptors, this is not a complete waste because this should also result in performance improvements, right? Descriptor caching, read ahead, and whatnot. This should result in, better performance because we're not waiting around for all these DMA operations. We can just pull stuff out of the cache, and we're issuing fewer DMA operations, but bigger ones. So that means, better utilization of PCIe, yada, yada, yada. So lots of advantages of doing this. The current descriptor format in Corundum is extremely simple. There's 16 bytes per descriptor with a 32-bit length field. Oh, wait, I have a duplicate slide. Okay, there we go. They're very small, 16 bytes with a 32-bit length field and a 64-bit pointer that indicates, where the data is located in memory. And they're transferred in fixed size blocks for scatter gather. So this means it's relatively inflexible, and there's extra overhead for small packets, right? Because if we're going to send, fixed size blocks of, 4 descriptors or 8 descriptors, so we can support packets that are broken up into 4 or 8 pieces. Well, if we have packets that are only in 1 or 2 pieces, then we're transferring all of this extra descriptor traffic for, no good reason. Unfortunately, we don't really have any other choice with the current queue handling logic because everything is in terms of, number of packets, basically. So there's a number of things going to have to be changed in order to support variable length descriptors, not just the actual parsing. But anyway, one nice thing about the current format is 16 bytes is tiny. So if you're sending a lot of really small packets, this is, or you're sending a lot of packets that are, contiguous, and if you're not taking advantage of scattered gather or sending a lot of additional metadata, these small descriptors end up being a very efficient description. So what I'm thinking about doing is kind of splitting the descriptors into 2 pieces. So the first one is the descriptor framing format. And this one basically indicates the type and size of each descriptor. And by splitting the framing format from the actual descriptor format, it means that the logic that's reading the descriptors from host memory and handing them off to the transmit and receive components, it doesn't have to understand the entire descriptor. It only has to understand the first couple of bytes, so it can actually pull out the descriptors. And if we have this kind of separation, then this also means that it becomes much easier to add additional capabilities to the descriptors, because we don't need to change the descriptor fetch logic. Right. So the idea is we're going to use the first 2 bytes. One of them will indicate the length in terms of these blocks of 16 bytes. And then the second one will indicate, the type. So in this case, we can support potentially a couple of different types of descriptors. Maybe you just want to send, these bare 16-byte, data segments. Maybe you want to, send a more complicated descriptor with, more header fields. Right. So this is kind of what I'm thinking about so far. We have, the descriptor header structure, which is the length and type. Then we have a descriptor block. This one can contain other fields, but that's just a placeholder, so 16 bytes in size. And then the actual descriptors, we have the descriptor header. We have potentially some additional fields, and then we can have multiple, 1 or more, or I guess 0 or more blocks that are describing, either a piece of data that needs to be transferred or other metadata fields or whatever. So that's kind of what I'm thinking the format could look like. And this can be extended to support things like inline metadata. So what you can do is have a data segment, which has the, if you want to send the data segment alone as a descriptor, you need the descriptor header, and then you could have flags, you can have the transmit checksum information, length, address, and whatnot. But then you can also send, say, a descriptor with inline data. So in this case, you'd have a descriptor header, you'd have flags for RDMA, whatnot, but need an opcode field somewhere. And then you can have, the number of data segments, and then the amount of inline data that's following those data segments. So you have kind of this header, and then you could have 1 or more data segments. And then after this, you can follow that up with some inline data. So this could be useful for things like LSO, where you're describing, a block of data that's much larger than a single packet, followed by a packet header, which you're then going to attach onto, the segmented data. So this would allow you to describe this type of a structure.
And
Brent, do you have some
given
comments?
I think this sounds great. And I was going to comment that I think this seems like it would work if I wanted to inline my entire packet subject to some maximum descriptor size.
Yeah.
And I just wanted to make sure that I wasn't missing anything.
Yeah, that's kind of the idea here. If you set data seg count to 0, then it's just inline data. So yeah, you should be able to do that.
And what's your planned maximum size here?
So at this point, I'm not quite sure, but I'm not quite sure exactly what I'm going to go with for the maximum size, but for looking at this little 2-byte header, if we describe if we use a length field in increments of 16-byte blocks, so this will support a descriptor of up to 256 blocks, which would be 4096 bytes, which that's kind of a nice number for various reasons. Now, would we support descriptors up to 4096 bytes? Probably not. We'd probably limit it like maybe 512 bytes or something like that. It's probably a reasonable number for that. 512 matches up with the PCIe max read request size. So, or at least a common value of the max PCIe read request size. So, but this could be exposed in a configuration register or something that the driver can read.
I think Mellanox lets you inline up to 256. I don't know why they chose that magic number, and I'm not 100% sure, but this sounds great. So sorry for interrupting, but thanks for the clarification.
No, that's fine. I mean, I'm pretty new to building NICs and whatnot, so people that have looked at a lot more NIC drivers and whatnot might have some input in terms of what needs to go into the descriptor and how to organize some of this stuff more effectively and what some of the considerations might be. I mean, I think if the NIC is reading everything via DMA, the exact structure doesn't make too much difference as long as the NIC is has the logic to pick it apart. Like, you don't need to worry too much about the alignment. But I guess on the flip side, the CPU does need to write it. So I've been trying to keep stuff aligned here in terms of, the size of the data, although maybe that's more important on some CPU architectures than others. The other thing that I'll mention too is that I want to get rid of this transmit checksum command field by implementing more self-contained checksum computation logic. It seems like most NICs these days don't require any input from the stack. They just need an input saying, yeah, this is an IP frame, please checksum it. They don't need a partial checksum. So right now, Corundum uses the, I guess this is an older checksum offload scheme where you provide a partial header checksum and then an offset to the start of the checksum region, and then an offset to where you want to write the final checksum. Or actually, no, you don't provide the checksum. You provide the offset to the start of the field, offset to where you write the checksum, and then you put the partial checksum in the header where it needs to go. And then the NIC goes and it checksums that, it sums over that portion of the packet and then inserts the checksum. If we're going to support RDMA, we can't do that because, we're not going to have the kernel networking stack saying, here's the header checksum. We're just going to generate a packet and then have to compute the checksum across that packet. So if we move to using, a more self-contained setup, then we can eliminate this 16-bit field here. And then we can either have a 32-bit length field, or we can have a bigger flags field, or we can have some other field. I don't know how much difference it makes. I know Mellanox uses a 32-bit length field, which I guess probably only makes sense if you're using, huge pages. And probably only makes sense for RDMA because you can't send, IP frames larger than, 64K. I'm not sure if that makes that much difference. I don't know if it makes sense to devote another 16 bits to the length field, or if it makes that much difference.
I wouldn't pay the overheads. You're not going to be sending a gigabyte in a single message.
Yeah, definitely under normal operations. And then well, it's not so much sending a gigabyte, it's sending more than 64 kilobytes. So if you wanted to send a megabyte, you would need more bits.
But doesn't your scatter gather list make it so that you just have to have another 8 bytes?
Well, yeah, so for the scatter gather, you would have to define each segment in the scatter list would only be
4K.
Well, so for RDMA and whatnot, it's common to use huge pages, and you can have, a couple of gigabyte huge pages, in which case you can definitely be transferring buffers of a megabyte in one shot without splitting every 4K.
You have a type in a flags field here. I mean, you could even just punt it off and say, 16 bits for now, and I'll change my flags if I'm using 1 gig.
Yeah, that's not a bad idea. Yeah. Okay. Yeah, I mean, I think for Ethernet applications, you definitely don't need more than 16 bits. But for RDMA, under, I mean, 64 KB is not all that big. So
yeah, I mean, I've definitely written RDMA applications that send 1 megabyte, and then I've written other RDMA applications that go through and segment that 1 megabyte up into 64K. But
right. I guess I can talk to some of my contacts and see what RDMA applications are commonly doing. Is this a common use case to do anything bigger than 64K, or if that's just really done?
The papers I've been reading, that people write applications that say, this is my file system, here's your 1 megabyte chunk, send it.
Right.
But so where I would say in the intermediate, we're getting back to some of the other things I said of, you have a driver, and your driver can take your 1 meg and segment it up into 64K as a starting point while you're waiting to implement larger chunks.
Right. Well, so the issue is that, yeah, you can segment into 64K chunks, but you can only fit so many of those in the scatter list. So at some point you run out of scatter list, and then you can't send chunks bigger than you know, however many scatter entries you have times 64K.
Yeah, I mean, but so even in, I think OFED, you can even correctly just send multiple entries in the worst case and still have it be correct.
Yeah, potentially.
I mean,
But
we're
like you're saying,
talking about
it's not a
RDMA
big deal
hacks.
to
I
have
don't,
a flag bit indicating, you know, how big the length field is or something. So
yeah, I think
that
that's a
could
good
be
point to
a
move
simpler
on.
way of doing that, because the, like, if we have a checksum field over here for whatever, that's going to be for, you know, Ethernet applications only. For RDMA, you're going to be using this descriptor header anyway with the opcode. And then I guess you could even use this flags field here to indicate, you know, whether to, you know, devote 16 bits or more to the descriptor data. I think the other thing too is that there are keys associated with things like the M keys or R keys. There's some other stuff that needs to be associated with the descriptors for RDMA. So it's possible that we're going to have to cram some more stuff into the data segment anyway.
I think you're totally right with that. And there's still the things, there's some RDMA commands that have extra data associated with them.
Right, the immediate
Like-
data, yeah.
I think you should just say RDMA is going to be a separate flag. And, you know, unless you're really worried about the extra area of having a separate code path for, you know, the RDMA DMA, it seems fine to me.
Well, RDMA is going to be a lot of additional area anyway, so.
That's kind of what I was thinking.
All right. So that about rounds it up for what I wanted to talk about today. If there's any more comments on the descriptor format or anything else, be great to hear from people.
What's the U8 reserved 0 for? Just alignment?
Over here.
Yeah.
Yeah, so that's
Or I
if you're
guess it would
sending
be-
if
I
you're
was looking at
sending
it
the data
with
segment
inline.
by itself, then you need the descriptor header attached to it. Just the first thing in the right, because this is the framing format, right? The first 2 bytes. But if the data segment is used, if it's not the first thing in the descriptor, then you can put something else here.
I see, but you don't want to. I was actually trying to talk about the other one, but that's interesting. On the inline data.
This one,
Yeah.
this U8 reserve 0.
Mhm.
Yeah, that was just because this is a U8. So U8 and then U8, so that keeps that aligned. So U16 is aligned.
Okay.
But yeah, this is just kind of what I'm thinking. We can certainly, you know, rehash this if it makes sense to do so.
I mean, I expect if that needs to be done, it's going to be entirely performance and benchmark driven.
Probably, yeah. Yeah, and also if you guys have any input on benchmarks and whatnot, I've basically just been running, you know, iPerf for testing stuff, which, you know, it works, but it's not really a comprehensive test. So that's definitely something I think that needs to be improved upon, so we can figure out, you know, what areas need to be adjusted.
Is the starting point. I have a student who's made a script that starts up multiple versions of iPerf in parallel so that you can actually run it on multiple cores.
Yeah, I kind of hacked something together for that as well, but you know, it might be interesting to see what you guys have.
Yeah, I mean, it's up on a GitHub repository he's already making anyways, so I'll just send a pointer to it.
Yeah, that would be cool. I guess the other thing that Linux has is the kernel packet gen setup, which is slightly different story because it doesn't execute, you know, the whole code path right through the whole stack. That's mainly just handing off descriptors or packets straight to the driver, as far as I'm aware. But that's definitely another stress test.
Yeah.
But yeah, I know you're also talking about latency and whatnot. I don't know if there's any particularly, you know, good techniques for measuring that and for characterizing that. That might be worth looking at.
I like this program from the Mellanox OFED distribution.
Curve.
Well, yeah, it's part of the perf test suite, but it's for a socket program. Sock perf? Yeah, I think it's sock perf.
Oh, okay, so it's in OFED, but it's not an RDMA program. It's something else.
Exactly. Yeah, it's sock perf is what I like for TCP ping pong latency.
Gotcha. Okay, sock perf. I'll see if I can pull that up. Okay. Well, definitely gonna have to give that a shot. That
So
could be a
one of the things they do right for measuring latency is they just sit there in user space and spin and pull. And so like ping, because Linux does weird thing with ping in the kernel that took me a year and a rejected paper, or maybe it was just a one-shot revision. Ping will tell you your latency is 100 milliseconds plus, and this, but like RDMA, the IB latency test will tell you it's 5 microseconds. This will tell you the Linux kernel is like 25 microseconds, which is like, I believe that. I don't believe why ping at 200 microseconds. So.
because there's some sort of coalescing thing going on for.
Yeah, I don't know what's going on with
ping,
ping.
whereas,
Ping
yeah.
is really not.
Interesting.
I was very surprised to learn how bad and inaccurate for latency ping is.
I mean, it seems like a lot of this stuff is just designed to run over the internet, and when you're going over the internet, 100 milliseconds, who cares?
Well,
I mean, unless you're Facebook or something.
And like maybe it's like legitimately trying to do DOS prevention or something. And so,
well, that's a
either
good
way,
point. I guess the question of where you're getting that 100 milliseconds, is that ping locally or is that ping on the other end?
oh, I said milliseconds. I meant to say microseconds, but it was
Okay.
still like 100 microseconds more than my actual application level latency.
I see.
And I don't care about ping's latency when I'm doing the stuff. I care about memcached latency.
Right. Yeah. So I was wondering with ping, is ping like the ping application being slow, or is it with the kernel turning the ping packet around on the other end that's being slow?
It's the kernel turning the ping packet. It's probably some
Okay,
sort of
okay.
special
Yeah,
packet
probably.
scheduling path where one kernel thread puts it in and some other kernel thread comes along and processes it.
Right. Yeah, that makes sense. Because who needs ping to be fast,
Yeah. That's all. That was my complaint, from a few years ago. But sock perf works. It's easy. It's Mellanox. So
All right. Sounds good. I'll take a look at that. All right. Is there anything anybody else wants to bring up? Anything else that we need to discuss today? All right. No comments on the descriptor format or anything else. All right.
my comment is it looks good. I like that there are scatter gather lists. I like that there's inline data. I like that there's flags. I don't really know what else I want.
Okay. Well,
Oh, one quick
we'll start with that.
things, but I'm not sure it is related with my own research because I may need to tune the packet throughput performance of Corundum, like the small packet performance. So what's your agenda of implementing the variable length descriptor? If you want to implement maybe a years later, I may need to do some quick hack over your
Right. Yeah, we
extended.
were talking about you doing some quick hacks. I mean,
Yeah, I know.
you're more than welcome to work on that, whenever you want and see what you can do. I mean,
Yeah.
it is definitely useful to have some idea of what the performance looks like of, other components of the system. So if you make a hack and you're getting X amount of performance, then that's probably what we're going to be able to expect with
Yeah, actually,
variable
I
length
have
descriptors.
like tried some hacks this week. I think prefetch would help a lot. Currently, it is bottlenecked for the RX path. It's bottlenecked in the descriptor fetch module, and so if we do batched prefetch, then the performance would improve. But I think then the bottleneck would become the completion write module because we do not have batched write for the completion.
Right.
So
yeah.
we need multiple hack here, and it is complicated.
All right, so I think the completion writebacks are probably less of an issue than the descriptor reads in the first place, because you don't need to wait for any completions to come back from the host, right? If you're reading something, you send a read request, and then sometime later you get the data back. If you're writing stuff, you just send the writes out, and then you're done, right? So Definitely reading stuff is a much bigger problem than writing.
Yeah.
But it would also make sense, I think, to make an attempt to coalesce the completion rights.
So one exception to that people have hit on some of these Mellanox nicks, I think, is that that is only true as long as you do not overflow your write combining buffers on your CPU. And that, so this was
Okay.
like Luigi Rizzo's PSPAT is a great paper on his website. I'd recommend that goes into this. But so one of the things he did is it was an Intel, 40 gig NIC or something. And he was deliberately trying to find the maximum doorbell rate of this NIC.
Yeah.
And once you exceed that, the amount that, let's say, your DMA engine can process, and it's not, the Intel NIC has a rate that's lower than the PCIe bandwidth. And so basically, as soon as you hit this rate by ringing too many doorbells, your CPU starts stalling again on writes.
Okay.
So it's throughput of these writes relative to what your NIC can sustain can still kill
Well,
you.
so this is from the CPU to the NIC, right?
Yes.
Okay. In this case, I think we're talking about the other direction, from the NIC back to the host.
Yeah, but I mean, if
right?
still, if you're doing
Completion write back.
it's the PCIe write, so in this case, sending it back, it was generating a lot of PCIe writes, but receiving packets will generate at least some PCIe writes. Hopefully, things can be batched, and if they're batched, you generally can do okay. Right, because
Right,
at some point you have to decide when to give. You have to re-add more RX descriptors. It's, I guess, not on the critical path. You could do it from another CPU, but eventually, if the amount of RX descriptor, adding RX descriptors, if that generates too many PCIe writes, you're gonna slow down again.
Adding descriptors shouldn't generate any PCIe writes except for when you add the batch and up.
Exactly, and so that's already batched, so that's not a big issue.
Yeah.
But if you were dumb and we're doing something where you explicitly got rid of the batching, or you're obsessed with low latency, and so you're doing everything one pack at a time. I wasn't trying to say that I think this is our bottleneck. I was just trying to say that writes can become a bottleneck in some scenarios.
Right.
I don't think in your current design and the Corundum design that is the case. I just was maybe being pedantic.
Right. Just in general. Yeah.
Yeah.
Well, I guess there's one optimization that you can make in the driver that I've seen other devices do, but I'm not a big enough expert on kernel development to implement this myself, and that's reusing the receive memory pages instead of reallocating.
Actually, this is what I have done for the user space, because we have a memory pool to reuse the things.
Right.
We also can do it in the kernel space, but
yeah, I think one thing that's nice is if you're just calling normal skbuff alloc functions, I'm pretty sure the Linux kernel is doing reuse for you to some extent.
Well, some of the other drivers that I've looked at are doing explicit screwing around with page counts.
I think you could probably get better performance doing that than what Linux is going to give you. But I think Linux is at least doing something to try to give you reuse.
Okay. Well, one thing I can tell you is that the Mellanox NICs get a much higher RX throughput through the kernel than Corundum does, and I suspect that's one of the reasons for that. Well, for 1500 byte frames, for larger frames, they're closer.
I think you are correct.
Yeah, so that's something that I would like to implement in the kernel at some point in the Corundum device driver, but that can be done down the road, I suppose.
Yeah, I think so, and that's something that's touching on what Jiachen and I are doing. So, we'll just tell you guys what we've done. Make sure we don't duplicate work.
Right.
We haven't done anything with it yet. We're sort of just ramping up. That's why I'm joining this meeting for the first time. Is I am about to start. Jiachen's been doing the driver development, and it's time for me to start doing it too. So.
All right. Well, you guys are going to be working mainly on the driver or on both the driver and the hardware?
Chechen's going to be touching a lot of the hardware too. I'm probably going to be doing more driver.
Okay.
Yeah, we are working the on NIC request scheduling and load balancing stuff. So we need to both touch the hardware.
Right. Okay. All right. Well, is there anything else that we need to discuss? Anything from the MLE side of things?
Today, I don't want to really talk too much as I'm a bit ill. However, I guess we kind of refocused as we kind of handed back to you the MPSOC XCDMA thing.
Okay.
And I think we revisited this, but just a very short thing. And next we will closer look at the Intel path. So I'm a bit busy with other stuff in this project right now. But there's some overlap here with Zhangjing's work. So we also have started to look at DPDK integration. So I guess it might make sense if we would just maybe send an email to the developers list so that we can share some thoughts on this.
Well, you can just send an email yourself. I mean,
yeah,
you don't need to wait
that
for
was
me.
just that was kind of me just thinking about this. So
Okay.
I will send a mail, or my colleague will send a mail. Then we can coordinate on this.
Did I just hear that you have a DPDK implementation?
No, we don't have it. We are working on it.
So I am also going to be working on that. So maybe I'll ping you on Slack once I'm starting to do something.
Yeah, okay. It would be great.
So Jiachen, she did the first thing that we've been working on is in this ICSI. It's an experimental educational user space network driver. And that's good for what we've been doing, but I'm going to look into DPDK too. So I'll ping you on Slack or something.
Yeah, so I'm on the Slack channel. And yeah, I will make my colleague join as well.
Okay, that sounds good. Thanks I'm glad we could meet.
Yeah, happy to. So if we can collaborate on this, we're happy. So for us, maybe to frame this is kind of a long-term thing. So we are not aiming at having something ready like next week. So this is something we do ongoingly until, I don't know, February or something. So there is no high pressure on this DPDK integration for us yet.
Well, I guess another thing to consider potentially is using XDP as the backend, because I know DPDK could use XDP sockets for interfacing with the hardware. Or at least I think it can. And then we can probably talk to the Axbird folks about what they've done for XDP sockets in the driver. So that's potentially another route. I don't know how that compares to using DPDK directly.
Yeah, so my quick take.
Go ahead.
Oh, you want to go, Ulrich?
No problem. I just wanted to say that these XTP guys were the Italian spin-off of the University of Rome, right?
Yeah.
Okay.
So I think my take is the first step. I would stick to just a clean slate user space implementation. I'm really scared of killing the reason I'm using DPDK by going back into the kernel to send packets.
Well, I think the whole point with AFXDP is to cut the kernel out of the data path.
I mean,
I guess maybe
I think if I understand AFX, I mean, So AFXDP, are we talking about just adding like BPF programs into your driver?
Well, I thought that was somewhat separate. So BPF
Okay.
programs are a different thing where you can
People,
do
I've heard
filtering.
XDP in this context, but there was
Right.
they're talking about the thing that's sort of like netmap, right?
Yeah.
Yeah,
Yeah.
I mean, so it's mostly cutting the kernel out, and that's great. But at the end of the day, you still call onto the kernel to go send your packets and to go read your packets.
I see.
And it's not really that big of a deal. But I also just kind of, my inclination would be to not do something weird. And
Right.
to just stick
Yeah, I
with
guess the thing
DPDK.
is for something like DPDK, it's a question of kind of exactly how you're attaching to the card. So the nice thing about having the kernel module is you can register additional interfaces that you can attach other things to for kind of configuration and management purposes. But if you're
Yeah.
going to attach the entire card to a single DPDK application, then all of that management and configuration and whatnot would have to go through your application.
No, that's the Intel way. That's not the Mellanox way. Are you familiar with how Mellanox implements DPDK?
It looked like from the time I spent looking at that, it looks like they're using their OFED API to interface with the NIC. So if we implement
100%.
RDMA and implement that API, then we can do that. But I don't know if that's something that we can do.
It's easier than
Okay.
that.
All right.
All you need is a way to make it so that the kernel won't touch some of your queues.
Right.
The Mr. Frankie wants to go outside. You need to make it so that your kernel won't touch some of your queues. That your user space can map those registers.
Right.
And then you need the RX path to steer packets to the DPDK queues separately. And so let's just as a straw man say you have a separate IP address and you hack up the driver so that it only touches half of the queues. That's where we've been starting for our DPDK implementation. That's what our ICSI implementation looks like.
Okay.
So it's very simple. It's very hacked together.
Still using the kernel module, but
100%. You must have the kernel module up and running and allocated, initiated IF up before you can run DPDK.
Okay. All right. Yeah. So if we can,
that's the Mellanox way. So
right. So if we can, find some, less hackish ways to do that, then we can certainly make some changes directly to the driver.
So the very quick thing to make it less hacky is to have a programmable way to set IP addresses to different pools of queues.
Right. Yeah. So that requires hardware.
Yeah. And so we statically partitioned queues into high and low and have 2 IP addresses. And so that's the hack for now.
Right. Well, we should make that less hackish.
Yeah, and I'm totally fine
that,
with
that I want to do
that.
at some point is to improve the ingress path basically and support some kind of flow steering. Because if we can do that, then that will allow you to do this sort of thing.
Yeah, and so
it's a flow steering, how much complexity you need in that block. You could take that to the max and do a whole RMT pipeline, but
I think you should.
I don't think. What?
I think it's actually way easier to do that than you think it might be, because there's open source RMT pipelines.
Right. But, okay. Well, send me some links.
Yeah, it's
we can take a look at it.
Yeah, I'll drop it on.
I mean, my main concern is more resource utilization, right? So if you're going to put something in there, it should probably be configurable in terms of, either bypass or not bypass. And then if it's there, how many resources are we devoting to that? But yeah, if there are some open source ones, that could be a pretty good option. But yeah, I guess like I said before, I mean, maybe you haven't been present for when I've said this, but yeah, all of the code that's going into the core of Corundum, it's got to be 100% Verilog. And it's got to be simulatable with the Icarus Verilog and Verilator. So that means no VHDL, no chisel, no spinal HDL, no HLS, 100% pure Verilog.
Yeah, I think this is a Verilog implementation. I need to find the paper.
Which does limit, potentially using other external projects. You can put whatever you want in the application section. I don't care. You want to use chisel in the application section. You want to use final HDL. You want to use HLS. That's fine, but just not for the core logic.
Yeah, there's this. I found the paper. I found their GitHub. I said Discord. I meant Slack, but
Okay. Well,
there's
send
at
it
least
over and we'll
something to
take a
look at.
Yeah, because I haven't really gone down that path too far because, if you're going to do that properly and you're going to integrate everything, you want to make sure that it's going to be flexible and scalable and whatnot. So,
Yeah. So this is pure Verilog that they've run on the NetFPGA.
oh, okay. This is not generated code, right? This is
I believe
this is
so.
not P4 FPGA.
I do not believe so. I believe this is handwritten code, but they evaluate it. It targets the NetFPGA.
Okay. Well,
so-
it's at least going to be a good reference. We'll take a
Yeah,
look
and
at
so
that then.
that's sort of my thoughts. Like, if you want to do something more with flow steering, like you don't need to reinvent the wheel for programmable packet parsing and matching.
Right. Yeah. Okay. And
And
potentially this could be used for some other stuff too, as opposed to just flow steering.
yeah, anything that's a P4 switch light, type application.
Right. Yeah. And then I guess then the other component too is you implement this, and then how do you expose it to the user? I guess that's going to require some additional kernel APIs and whatnot. And I guess
I
there's
would do it
potentially a
all
couple-
user space.
Well, initial implementation all user space.
I don't see any reason this needs to be in the kernel.
There aren't flow steering APIs in the kernel.
Oh, so again, let's go back to sort of the Mellanox way. To do flow steering in Mellanox, maybe it goes into the kernel, but you have to use their custom user space program as a starting point
I see.
to
Okay.
even impact flow steering in the kernel. But
Okay.
I mean, you're right but I think there's even the question of, is that flow steering in the kernel actually change anything in the kernel? Or did it just change something on the NIC? I mean, maybe it does a little bit of both. I'm not sure exactly.
Well, by saying kernel, I mean inside the kernel module. So,
Yeah.
does it involve implementing the ETH tool APIs for flow steering and then push that configuration to the NIC?
So
Or
I almost suspect they just shortcut it all, and because it's just a simple interface of like, here's your queue number, and give us some IP addresses and port numbers, and we'll send to this queue number. I think that might all just bypass the NIC entirely.
so it's done on the RX path after the packet comes out of the NIC.
I'm sorry, it's done on the NIC. The
Done on the NIC, okay,
configuration,
yeah.
I don't think touches the kernel, because I think the
Well-
configuration just speaks to the everything to the Mellanox NIC does go through the kernel eventually. I guess that's your point.
Right. I mean, are they using standard kernel APIs for that? Like, I think there are some like ETH tool APIs or whatever for setting up this kind of flow steering stuff. So you implement it in the hardware, and then you also have to implement those APIs so you can actually configure it using standard tools instead of doing something non-standard. But I guess this is a path you can cross a little bit later.
So my experience with
as long
ETH
as
tool,
the RMT pipeline comes up by default, passing the packets through with RSS or whatever.
yeah, the ETH tool interface for flow steering on the NICs I've used is different and unique for every NIC, and there is no standard. It's a pain. So
I guess to some
that's-
extent that's not surprising, because there's probably pretty significant differences in the capabilities of those NICs in terms of what they can do for flow steering. So,
exactly.
all right, well, that's good to know. I'll take a look at that code at some point, I guess.
Yeah,
It might take
I'm not even sure how public they want the code to be, but they put up an archive paper, and I followed them on Google Scholar, and so I found the archive paper, and their archive paper contains a link to a GitHub. So that seems pretty public to me.
Okay, well,
But so I'm friends with Gianni, one of the guys on this paper, and so if you have any questions or something,
yeah.
I know he's pretty friendly and willing to talk to people about this. So
Yeah. Well, I mean, again, it's at least a good reference, even if we can't use it directly. It looks like they're using some Xilinx IP, so we would have to rewrite that probably.
My hope is that that is for the net FPGA specific stuff and not for their.
Well, it said the Xilinx CAM IP, and then
Oh.
also fall through small IP from net FPGA. So, I mean,
Yeah,
you
well,
could
no,
probably
now
just-
now you're right. If the CAM IP is definitely their lookup table, then
right, yeah.
Okay.
Because that's the thing. We're working on Stratix 10 support right now. So whatever code that we have here is going to run on both Xilinx and Intel devices and potentially other devices. So so we can't
What's
use
your
anything that's Xilinx
experience
specific.
with how much are you paying in terms of overhead having to write your own, say, CAM IP rather than use the Xilinx one?
Well, what do you mean overhead?
Like,
Development overhead or resource consumption overhead? or
yeah, like
timing overhead,
the
or-
resource consumption, because presumably you're not going to get it as good.
I don't know. That's not something I've literally done nothing with cams. So, we'll have to take a look at that, I think. That's my concern about this sort of thing is, how big are the cams and whatnot? How many entries can you put in there? How many resources is that going to take up?
Yeah, I mean, I think my expectation is for DPDK type applications, you can probably get away with, tens of entries to start with.
Right.
At some point you're going to be limiting someone's research project, maybe even mine, but I think, a small entry, if that's what's fit, I think is perfectly reasonable.
Right. Well, I mean, the idea with the application section is if you want to do something more complicated, well, just ignore what's in the core data path, bypass that, and drop your custom implementation in the internal application section, and then you're good to go. So.
Sounds good.
All right. Anything else to discuss? It looks like most people have cleared out of here since we're it's almost 11 a.m. now.
Yeah, sorry if I derailed your agenda, but I really appreciate being able to talk about
That's the
things we
point
talked
of
about.
these, right? I mean, I can certainly yak about whatever, but the point is to get everybody who's interested involved and get some feedback and direction and whatnot. So that's perfectly okay.
Okay, well, that sounds good. I guess I'll drop. I'll be here in the next 2 weeks. I'll be on Discord or Slack. Gosh,
Not a fan of Slack.
I play video games. It's not that I'm not a fan of Slack,
okay.
but my default is Discord.
Yeah, okay.
Okay, well, thanks. I'm going to drop off.
All right, sounds good. Glad you could join us. Ulrich, were you going to say something or?
Well, I just had a quick question regarding the CAM block from Xilinx. So the last time I had contact with it, it was just what is it? This pre-compiled container DP something. So it was not available as source code or configurable or anything. But maybe there is something released to academia which I don't have access to.
So they have some white papers on cams, and it's possible
That's right.
that the more recent IP is just one of those application notes but tweaked.
But are you aware of this? You are aware because you asked if we are the guys working with it. The Xilinx open source TCP IP implementation.
Oh,
and
the
that
HLS?
also uses, yes, right, the HLS thing, and that also uses, I think, in two areas. There is a CAM block in this, and it's not source code. It's definitely a DPC. Is it correct? DPC? Design partition something.
I don't know. I've never worked with HLS, so I'm not sure what the terminology is.
No, that's not an HLS thing. That's the Vivado way to provide a precompiled blob, and you can choose if you want to provide source code or synthesized or pre-placed or whatever, and you can export this and share this with others.
I see.
Yeah, something like maybe think of it as a Vivado internal data structure dump.
Oh, the design checkpoint.
Yeah,
DCP?
DCP it was. Right.
Ah, okay. Really? They're pulling in a DCP from
Yeah. So
from
the
the
DCP
HLS
is
code?
part of the GitHub, I guess. And
Wow, that sounds pretty nasty, but okay. Interesting.
yeah, especially if you call it open source, and actually you cannot really recompile it into any other FPGA because
You probably
I
can't
don't know
even
that
compile in a different version of Vivado because of that, I would think.
maybe right, maybe.
Interesting.
So that's you have to dig into this, and then you'll find these DCPs. So if this is the same thing, then I'm not sure if you can actually find out anything about the implementation
Well, so
other than the
that
white papers.
repository
That's
links
right.
to this thing. So I haven't used here. Let me send you this link real quick here. There we go. That's the app note that was linked from that GitHub page. That looks like one of the app notes that I looked at previously. So I actually just, out of curiosity, read over the app notes and kind of implemented, something similar to what they described. So I have a little
Okay.
a repository. Where do I have this here? Let's see. Okay, so this was like years ago. I put together this repository with, basically implementations of what was described in their app notes, but I've never used that code for anything. So I don't know how well it works. It may need some pretty significant tweaks. I don't know how scalable it is. I don't even know if it works reasonably well on the Intel devices. So with this sort of thing, you're basically trying to make the most use out of whatever primitives are available on the device. And I think the primitives on the Intel devices are a little bit different. I'm not sure how different in terms of their capabilities. So I'm not sure how much things would have to be tweaked in order to work there. Not sure about
Okay.
that. But you got the
Yeah, I
links?
don't know either. Yeah, I got the links, and
Okay.
I got it open in my browser.
Okay. Just making sure, because whenever you quit out of Zoom, then all the links go away. So
yeah, that's really bad. However, yeah. Yeah, cool. Yeah, thanks for sharing this. I'll have a look. The Verilog cam.
Yeah, because I guess if we're doing anything with DPDK or any sort of user space networking thing, we're going to have to implement some sort of flow steering in hardware, I think, anyway. Otherwise, they're not really going to use many RX queues. So,
yeah, I guess we already had the discussion about enabling the application to do some steering.
right.
And I guess you mentioned that you had the plan to provide some API for this in the future anyway.
Yeah, I mean, it's like a kind of a to-do thing. It's like, yeah, let's do this.
Right.
I don't know what it's going to look like. I don't know how it's going to work. I don't know what its capabilities are, but this is going to make sense at some point. So, if you guys want to help kind of steer that discussion and figure out what sort of capabilities that's going to need to have, then let's make it happen.
Yeah, maybe we'll start with a little thing, and we could discuss this next meeting, like in 2 weeks.
Right.
So,
okay.
So we started discussing this internally, and I think that's not the long shot, but maybe the short-term way to do this. Kind of reusing what is already there in the following modules, so that we don't have to change all the architecture and interaction with drivers and so on, but just add some little functionality there. So I started to draw some block diagrams, and I guess we can finalize this until next meeting.
All right. Well, and again, if you guys want to meet, more often, either with me or with, potentially other people, that can certainly be arranged if it would, help accelerate development. So, just let me know.
Yeah, that's highly appreciated, and yeah, as you know, we will reach out to you.
All right.
And Yeah, let's see. If we are faster than I think right now, then I could also just send this to the mailing list, right? So that's okay too.
Yeah, if you have something you want to send, then just send it. No
Right.
reason to wait.
Correct. And then we can go over this again in the next meeting anyway. So I think we will we'll come up with a proposal with maybe the non-vision way of adding something, but which will be enough for our purpose. But if we are starting to implement something, we would also be happy to start something that would be more than what we need just to enable other people's need. Yeah.
All right. Well, that sounds good.
Cool. Yeah. So we are getting much from this project, so we can also provide something back, right?
Well, I mean, if you guys are providing stuff back, then I'm, definitely motivated to help make that happen.
Thanks,
Like I was
Alex.
telling some of the people in my research group, our interests are very well aligned at the moment because, we're both trying to get stuff running on the same platforms. So,
Right.
if we can work together on that, then that's better for everybody. So
I think so.
And does
Good.
Joachim have anything to add? He's just been here on mute the whole time. Or is he, or have you not been able to figure out how to get yourself unmuted?
No,
maybe
no.
that's his holiday
I
mode.
made it.
You're not double,
I
triple,
guess
quadruple muted this time around. Okay, that's good.
No. I'm actually doing something else at the same time. So
Okay, just listening in. That's fine.
I didn't detect a direct question to me, so I kept my mouth shut.
Well, I was wondering
Um,
earlier about firmware updates and whatnot on at least the StratX 10 devices, if that's something that you guys are going to be working on, or if that would be somebody else at MLE. I don't know.
Yeah, well, I guess I think I didn't hear everything. In the meantime I was away and so on. But yeah, basically I guess we need a mechanism there.
Okay.
But Ulrich, I don't think we thought about the details here, or even the
No, not yet.
hardware side.
Right. Yeah. Because well, I guess we can revisit this discussion real quick for a couple of minutes. You guys have a couple of minutes, right?
Yeah.
Okay. Yeah. So, right. So with all of the current Xilinx boards, the way the firmware update is set up is it's just bit banged. So the user space application just directly toggles the pins on the flash chip, which is directly connected to the FPGA. So that's nice and simple. You don't need to put much on the FPGA for it to work. And the FPGA doesn't really sit in between the FPGA or the flash chip and the PCI Express interface. There's nothing weird going on there. But on the StratX 10 devices, things get a little bit more complicated for a couple of reasons. One of them is the StratX 10 devices have this SDM block, the Secure Device Manager. I don't know a whole lot about what goes on inside of that, and I don't know what involvement that has in terms of interfacing with the flash. Like, I don't know if you can directly access the flash pins or if you basically have to talk to the SDM and have it access the flash on your behalf. I'm not sure. So that's a potential concern with the StratX 10 devices. The other thing is how the boards are actually designed. So something I mentioned before is that for whatever reason, Intel likes adding these Max 10 FPGAs on their boards. Now, if it's just for USB JTAG, yeah, that's fine. But on some of their dev boards, the Max 10 FPGA sits between the configuration flash and the main FPGA on the board. But apparently that's not always the case. So, for example, on the StratX 10 MX development kit that I have, the FPGA, the StratX 10, is directly connected to the configuration flash. So presumably there's no issue there as long as you figure out what you need to do with respect to the SDM. But on the StratX 10 DX development kit that I have, there is the Max 10 that sits in between the FPGA and the configuration flash. And the interface between the Max 10 FPGA and the Stratix 10 is Avalon streaming. So it's a one-way interface. So the FPGA, you cannot access the configuration flash. So you can't read it, you can't write it. It's just the Max 10 transfers the configuration data into the Stratix 10, and that's it. And they don't have any other interfaces between the two for configuration or anything. So the only way to update the firmware on that thing is over USB JTAG, which is just stupid. The Bitware board that I have, the 520N MX, has a similar setup where they have a Max 10 that sits in between, but they have an additional proprietary, ad hoc protocol that they put together between the Stratix 10 FPGA and the Max 10 that presumably allows access to the configuration flash for updates. I have the source code for their firmware update application, which interfaces with their their HDL design basically. So I have some idea of how it needs to work on their board in terms of updating the configuration flash through the Max 10 part. Presumably for your board, if you can get away without having to put a Max 10 FPGA on there, you're probably going to go that route. So if you can do a direct connection, that's probably going to save on the BOM, what parts you're putting on there. So presumably you would want to do something similar to what's on the Stratix 10 MX development kit. But like I said before, I don't know what needs to be done on the SDM side of things. I don't know if you're going to be able to use the same kind of bit banging protocol for writing to the flash. I'm also not sure how much research you guys have done looking into the capabilities of the Stratix 10 and whatnot.
Well, independent of the specific device, I guess update procedures are always critical,
right?
Especially if the devices are run by non-trained personnel, right? So if those people are not aware of that there is something running in an FPGA, then and you're doing a firmware update that might break your card, then
right,
things get critical. So I don't know how the other network
or something, yeah.
Yeah, and I don't know, they do something else that the PC freezes up and then that's the card, right? Just while they are flashing firmware. I don't know how the other people do this. I think they will do some golden image type of backup things, which I would definitely do. Otherwise, yeah, the ratio about RMAs because of brick devices are just too high. So I guess there is a lot of things to think about, and if then I don't know if I really want to go with bit banging in such critical path. So there, it's not about latency or performance or bandwidth or anything, but it's just about consistency of the data written into the flash.
Right. Yeah. Well, it seems like there's some kind of several different things that need to be picked apart here. So the interface to the flash, bit banging, I don't think really makes much difference one way or the other, because you can always, do a verification pass and read everything out and make sure everything read correctly, to make sure that that part of the programming completed. And bit banging versus doing something else, I don't think is going to make all that much difference, because you can always power cycle something in the middle of the process and break things, whether you're bit banging or
right.
having the card DMAing stuff. Either way, there's a potential to brick it. Now, doing some sort of a golden fallback boot kind of thing, that definitely seems to be pretty common, where you load 2 bit streams in there, and then it's either loads the golden one first or second, and then there's some sort of a fallback which will trigger the other one if something doesn't work. But the problem is usually not working means that the CRC fails, not that the design loads but doesn't work, if you know what I mean.
Yeah,
like
that's
if you
right.
load the wrong file on there and it doesn't bring up the PCIe interface, well, from the FPGA standpoint, it booted up, right? So everything must be good. But then you can't reprogram it because it doesn't have the PCI Express interface working or something. So
no, that's right. But I guess that's another thing to prevent people from loading incorrect bit streams.
Right, yeah, so this
that
is
could be
where
dealt
maybe
other-
instead of loading the bitstream raw, you wrap it in some sort of a container, and then you have some software that checks to make sure that it's appropriate for the hardware that you're trying to load it on and whatnot.
Right.
So I haven't done anything like that in Corundum yet, but I think that would be a good thing to take a look at some point. But right now I just have it set up so you can just load the bit file directly, because that's what I'm doing most of the time. I build something and then I have 10 machines, so I just, flash all 10 cards and then we're good to go. But then all the cards are also plugged in via USB, so if something fails, then I can always just go over JTAG and fix the problem. So it works well enough for research type applications, but for something production, it could probably use some polishing.
Yeah, right. Yeah, I think anyway, from a PCI Express boot up performance point of view, we will need to do CVP anyway. So all the flash loading thing would just be for the base image.
I see. Okay.
So it should be a rare case where we need to do this, but however, it might, and so it will happen. So we need to think about this.
CVP, because I know, well, maybe I need to do some more reading on this, but I think you can do what they call it, the autonomous PCIe interface. So basically the PCIe interface comes up during the load operation.
You're right. So I guess that's a newer feature, right? So the last time I worked with PCI Express on Intel, and it was on Area 5 or something. So it was not available back then.
Right. Well, there's a huge difference with these tiles now, because they have so much hard logic in the tile.
Right.
That they can support
so
that.
We definitely have to revisit this. So my original thoughts were that we go with these base image and something loaded by the driver afterwards, but we'll see. I think that's not finalized yet, but we have to do this soon, as otherwise we can't build the PCB, right?
Right. Yeah, that's true.
Yeah.
So did you guys finally get the Stratix 10 dev board on your end?
No, we haven't gotten. We haven't. No, not available yet.
Okay.
So I think we will get.
So like
one,
I said, if you want access to either of the boards that I have here, let me know. We can set that up.
Yeah, I guess we'll talk about this this week, and I think generally we should do this anyway. Actually, just to line up one setup where we test on, right? So because I think that would make things much simpler to exchange the design when we're running into an issue, bringing your code up, for example.
Yeah, that could potentially make sense. At least for the Zinc MPSoC, that probably makes a lot of sense. For the other one, we'll see. I mean,
okay.
It's one thing if we have the same dev board at both locations. It's another thing if we have different things. So it's like, I think between you and me, I don't think either of us have any of the Intel dev boards in common. So
right, that's right. So I guess we will get the GX, the Stratix 10 GX dev kit.
Right.
And you got the DX, right?
I have 3 different Intel dev boards right now. Well, I guess actually.
But one was the Bitware one.
So yeah, I have a Bitware board with a Stratix 10 MX. I have a Stratix 10 MX dev kit, and I have a Stratix 10 DX dev kit. So the DX has a totally different PCIe interface. So I'm setting that one aside for now. So that leaves us with the other 2 Intel Stratix 10 MX boards, and they are almost exactly the same part. They both have 16 gigs of HBM. The only difference is the speed grade. I think one's the Stratix 10 MX is the fastest, and then the Stratix 10 MX dev kit is the fastest. The Bitware board is like the middle speed grade, a -2.
Okay. Yeah, we'll see. So I guess
Oh, I was also doing some reading on H tile versus L tiles. I was trying to figure out what parts have H tiles, what parts have L tiles, what is the difference, yada, yada, yada. Eventually, I figured it out by looking at the data sheet that actually lists the part numbers. Basically, any StratX 10 part, you can pick whether you want H tiles or L tiles. And the only difference between the two is its transceiver speed. So from PCI Express, from that standpoint, that doesn't make much difference. Because the features are basically the same.
okay, that makes sense now. Okay.
Yeah. I was trying to figure that out. I'm
But-
like, but so if I get an SX part, then it's an L. If I get a GX part, then it's an H. Like, what? No, but so anything other than the MX and the DX, you can pick which one you want. Or maybe it's just the SX and the GX. Maybe the TX is always H. I don't know.
Yeah, because I was also irritated, and I just asked our Intel guys, and they confirmed. But yeah, so I was
The
reading
documentation is terrible.
It's really bad. Well, I think it's more like so. And you and me probably that's the same. That's true for you as well. So I've been familiar with Xilinx documentation for 10 years now, no more than 10 years, and with Intel documentation every now and then. Or back then it was Altera, right? And now it's Intel. So the style changed, and how they put things together changed again. And I don't know where to look at, and where to search for something.
I mean,
so that's really
the thing that annoys me the most is that there's just little bits and pieces of information that would be very easy to list in tables here and there, but they just don't show it. Like in their product tables, can you just tell me which tiles these parts have, right?
yes.
Just put that in the table so I can go look at those data sheets.
Or if there is an algorithm for it, describe the algorithm rather than 20 pages of tables.
Right. Yeah. I mean,
like you just said. So if it's connected to speed grade, so okay, just tell us, because that's where I found it very weird.
It's like just one paragraph or something explaining what the difference is, or yeah.
Yeah, and everywhere you when you are looking for it, it says H or L tile, and I was like, okay, which one now? And
It's, they could just add a note, depending on the part number. These chips can have either.
Yeah, and there is a speed grade part number as well. So if this is kind of interconnected, so then it's kind of the same.
Speed grade?
I guess there is a speed grade portion in the part number as well, which also affects the transceiver speed.
Oh, yeah. I would need to take a look at that. Yeah, I know the transceivers have a speed grade, and then I know the H tile and the L tile, I guess, have slightly different transceivers. So the H tile is good to like 28 gigabits a second or something, and the L tile is good to like 12, something like that.
Okay, and then within this max number
from the transceiver speed grade.
Okay, so I mixed that
Just
one
to complicate
up,
things.
possibly.
I mean, the transceiver speed
Right.
grade is usually like 25 versus 27 versus 28, something like that. It's not going to be like 12 versus 25. That's
Right.
That's different.
Yeah, but it's enough to be able to do long range with FEC, or you won't be able to do this. Yeah, but if you so still you have to look at it, because otherwise you might not be able to do 25G with forward error correction, because then you need 27 point something gigabits.
Oh, I see. Yeah, the KP effect, right? That's
right.
Faster line rate. Well, you guys are doing 40G interfaces, right? So it's just 10G.
Yeah, we do 4 times 10G in this project. In other projects, we do 25. Yeah, a lot of 25G. I guess we are looking at 40G soon. Maybe doing some 50G as well. Let's see.
Right. Yeah. Okay. Yeah, because I was originally, when I was putting the hard tile models and whatnot together, I was originally just doing everything for the H tile. But then I sat down, I'm like, what the heck is the deal with this L tile thing? But yeah, so since it seems like you could use either of them, and it sounds like probably for your application, the L tile is probably going to be the one you'll use, and I might as well support both. So fortunately, they're very similar. There's just a couple of minor differences between the two. So couple of parameters here and there to support both, and then that will save us some headaches going forward.
Yeah, especially because other people will be also not correctly knowing what they will use, I guess.
Right.
So it makes sense to support both then. Cool. So I guess I kind of have to drop off now. I just got called. And
All right. Well, we can revisit, some of this
back.
discussion later on as
Yeah,
necessary.
we'll do so.
All right.
So great, and thanks for your great help and support.
Yeah, no problem. Well, hopefully this will be a mutually beneficial setup here. So that's the
Hopefully,
goal
yes.
anyway.
Right. Good.
All right. Well,
so have a good day.
sounds good. Have a good night, I guess, for you guys, right?
Yeah, thanks.
All right.
Thanks, yeah.
See ya.
Bye.
Bye.